cold you feel on a winter morning is lying to you. What your body calls cold is heat leaving through contact with matter. No matter, no cold. Space is almost entirely matter-free. NASA has measured the baseline temperature of the cosmos to within 1,000th of a degree. It is colder than liquid helium, colder than anything on Earth, and it fills every direction of the observable universe without exception. Most people have never been told where that cold comes from. The answer arrived by accident: a radio antenna in New Jersey, and a signal 2 engineers spent months trying to explain away. What they found was the oldest light in existence, the last echo of a universe born in fire, stretched and cooled across 13.8 billion years. We will trace that cold to its source, weigh it against everything that burns, and follow the story to the end of heat itself. Subscribing helps this channel keep making journeys like this one. The universe has a temperature. Let's find out what it cost. Let's begin. Most people, if you press them, will tell you that space is cold. Not just cold, impossibly cold. The kind of cold that kills in seconds, that freezes everything solid, that sits at the absolute bottom of whatever scale you care to use. And they say it with the particular confidence of someone who has never had to question it, because it seems so obvious that questioning it would feel strange. Space is dark. Space is empty. Of course, space is cold. The problem is that this is not quite right. Not in the way most people mean it. When you ask how cold space is, you are treating space as though it were a substance. Something with thermal properties, like water, like metal, like the air in a room. But space is not a substance. The vacuum between stars is not filled with cold material pressing in from every direction. It is filled with almost nothing at all. And asking for the temperature of almost nothing is a question that physics can only answer if you are very precise about what you mean. Consider what you are actually asking when you describe anything as cold. On a January morning, step outside and feel the air against your face. Molecules of nitrogen and oxygen, billions upon billions of them, crammed into every cubic centimeter of the atmosphere around you, are colliding with your skin at speed. Each collision transfers a tiny quantity of energy away from your body. Your nerve endings detect the loss and send a signal upward. The signal gets labeled cold. It feels like a property of the air, but it is not a property of the air. It is a description of what the air is doing to you. Cold is not something that exists out in the world, waiting to be encountered. Cold is the experience of energy leaving your body faster than it arrives. Strip away the thing doing the taking, and the cold goes with it. This distinction seems almost philosophical until you carry it into space, where it becomes the difference between a common misconception and an accurate understanding of the thermal universe. Take away the molecules. Take away every particle of gas for millions of miles in every direction. What remains is not cold air. It is an absence of matter, of contact, of any mechanism by which energy could be stolen from you through touch. And yet things in space do have temperatures. Objects heat up and cool down. Spacecraft bake and freeze. Planets are scorched and glaciated. If the void cannot conduct cold into anything, how does anything in space become cold at all? The answer lies in what temperature actually is, not as a sensation, but as a physical measurement. And understanding it properly requires going down to the level where the physics actually operates. Temperature is a measurement of motion. Specifically, it describes the average kinetic energy of the particles that make up a substance, how fast the atoms or molecules within it are moving. In a gas, hot means fast. The molecules of hot air are moving more rapidly than the molecules of cold air, and when those fast-moving molecules slam into your skin, they transfer more energy per collision. Your body reads that as warmth. Cold air, with its slower molecules, transfers less energy per collision, so your body reads that as cold. The entire mechanism, from the physics upward, is a story about particles moving and hitting things, which is why the concept begins to dissolve the moment you try to apply it to the vacuum of space. A cubic centimeter of air at sea level contains approximately 25 billion molecules. That number gives you a sense of how dense even ordinary air is at the atomic scale. Every breath you draw pulls in this enormous swarm of particles, each one participating in the thermal conversation your body is constantly having with its environment. Now consider the interstellar medium, the material that fills the space between stars. The typical density of interstellar space is approximately 1 atom per cubic centimeter, sometimes less. Compare that to the sugar cube of air, 25 billion versus 1. The difference is not large, it is not even vast. It is so extreme that no analogy of scale captures it honestly. A conventional thermometer placed in that environment would be useless for measuring the temperature of space. The thermometer works by allowing heat to flow between itself and the surrounding medium until they reach the same temperature, a state called thermal equilibrium. But in a near-perfect vacuum, there is effectively no surrounding medium. There are not enough particles present to transfer any measurable quantity of energy to the instrument. The thermometer would register nothing about the void around it. It would register its own temperature, whatever that happened to be when you placed it there, and then drift slowly toward a new value determined entirely by a different process. A process that has nothing to do with particles hitting anything. Here is where the physics makes a distinction that most everyday intuition never has cause to make. Temperature is what physicists call an intensive property. It describes the state of whatever matter is present, the speed of the particles, the energy per particle. It does not depend on how much matter there is. Thermal energy, by contrast, is an extensive property. It depends on both the temperature and the amount of material present. A tiny amount of extremely hot gas might carry almost no thermal energy at all because there is so little of it. A large amount of cool gas might carry an enormous quantity because there is so much. This distinction matters enormously when you try to describe the thermal environment of space, and it exposes a confusion that runs through almost every popular account of the subject. The interstellar medium, the sparse gas and dust between the stars, exists in several different states, some of which are technically at very high temperatures. Regions of interstellar gas heated by supernova explosions or by the ultraviolet radiation of young stars can reach temperatures of hundreds of thousands of degrees by the formal definition. Particles within that gas are moving at velocities that correspond to those extreme temperatures. And yet, if you were somehow placed inside such a region, you would feel nothing, no warmth whatsoever. Not because the temperature is not real, but because the density is so vanishingly low that there are not enough particles present to transfer any significant energy to you through contact. The gas is hot, but it carries almost no thermal energy, and it is thermal energy, not temperature alone, that you feel. This is one of the most important conceptual distinctions in the physics of space, and it is almost never mentioned in the places where people learn about this topic. Hot does not mean warm. A region of space can be technically millions of degrees and still leave you completely cold, in the practical sense, because there is simply not enough matter there to make the temperature felt. So when someone tells you that space is cold, they are reaching for a truth that is more complicated than the shorthand suggests. The vacuum of interstellar space is not cold in the way a freezer is cold. A freezer is full of cold air, slow molecules pressing against everything inside it, draining thermal energy through constant contact. The vacuum has no such material. It presses against nothing. It takes nothing. It simply exists, or rather, it barely exists at all, being very nearly nothing. What this means in practice is a conceptual shift that the rest of this journey will build upon. Stop asking what temperature space is. Start asking instead, what temperature will any given object become if you place it in space and leave it there long enough? That is the right question, and the answer, it turns out, is not arbitrary. There is a flaw, a temperature that every isolated object in the universe will eventually approach, no matter where it is, no matter how far it sits from any star or galaxy. A baseline so fundamental that it is not really a property of any particular region of space, but of the universe itself. It was set at the very beginning of cosmic time and has been falling, slowly and continuously, ever since. That number, 2.7 Kelvin, barely above the coldest condition that physics allows, is not just a measurement of how cold space is. It is a fossil. It is the thermal remnant of the moment the universe was created. And to understand where it comes from, you first need to understand the one mechanism that actually governs heat in a vacuum, the only process through which anything in space loses or gains thermal energy at all. There are three ways heat can travel from one place to another, and two of them require matter. The third does not. In the vacuum of space, only the third one operates. And once you understand what that means, the thermal world beyond Earth's atmosphere becomes something entirely different from the cold, dark emptiness most people imagine. The first mechanism is conduction. Place your bare hand on a metal surface and feel the cold. Thermal energy flows directly from your warmer hand into the cooler metal through physical contact, carried along by molecular vibrations passing from one atom to the next. The faster vibrating molecules of your warm skin collide with the slower vibrating molecules of the metal and transfer some of their energy. The metal's temperature rises slightly. Your hand's temperature drops slightly. Conduction also explains why materials feel different at the same temperature. Touch a piece of wood and a piece of steel that have been sitting in the same room for hours. Both are at room temperature, but the steel feels cold and the wood feels neutral. The difference is not temperature, it is conductivity. Steel pulls heat away from your hand far more efficiently than wood does. Your nerve endings measure the rate of energy transfer, not the absolute temperature of the thing you are touching. In space, conduction is irrelevant. Nothing presses against you. There is no surface to touch, no material to transfer heat through contact. The second mechanism is convection. This is heat transported by the bulk movement of a fluid, a gas or a liquid circulating and carrying thermal energy from one place to another. It is the mechanism behind weather. Warm air near the equator rises, cool air flows in beneath it, horizontal pressure gradients develop, and the result, over scales of thousands of miles, is the global circulation of Earth's atmosphere. It is the mechanism behind ocean currents, which transport heat from the tropics toward the poles and moderate the climates of entire continents. It is also the more intimate mechanism of a breeze on a warm day. Moving air carries the warm layer near your skin away and replaces it with cooler air, continuously renewing the temperature gradient between your skin and the surrounding environment and accelerating the rate at which you lose heat. This is the wind chill effect, not a change in the actual temperature of the air, but a change in how efficiently that air removes your body heat. Convection is also what makes Earth's atmosphere so effective as a thermal moderator. Step from direct sunlight into the shade, and the air temperature around you barely changes, perhaps a degree, perhaps two, even on a hot day. The reason is that the atmosphere has already mixed the sunlit air and the shaded air together through convection, smoothing out any temperature difference that sunlight alone would otherwise create. The sharp, savage boundary between heat and cold that direct radiation would impose on a bare surface is blurred into something gentle and gradual by the constant circulation of air. In space, convection does not exist. There is no fluid to circulate, no medium to flow. The thermal smoothing that the atmosphere performs invisibly and continuously on Earth's surface is simply absent. Whatever thermal difference radiation creates is not buffered by any subsequent mixing. It persists, sharp and complete. The third mechanism is radiation. Every object with a temperature above absolute zero emits electromagnetic energy in the form of photons, particles of light. Not necessarily visible light, but light in the broader sense. Energy propagating as waves across the electromagnetic spectrum. At body temperature, humans radiate primarily in the infrared, invisible to the eye but detectable with the right instruments. Hotter objects radiate at shorter wavelengths, carrying more energy per photon. Cooler objects radiate at longer wavelengths, carrying less. The spectrum of radiation an object emits, and the total quantity of energy it emits per second, depend on its temperature in a precise and well-understood way, described by the physics of what is called a blackbody radiator. What makes radiation categorically different from conduction and convection is that it requires no medium. It travels through empty space as naturally as it travels through air. A photon emitted by your skin does not need anything to carry it. It propagates outward at the speed of light, through whatever lies in its path, whether that is air, glass, or the vacuum of interstellar space, until it encounters something that absorbs it. This is the only mechanism of heat transfer that operates in a vacuum. And that single fact transforms the thermal physics of space into something radically different from anything your everyday experience has prepared you for. In space, every object is simultaneously emitting radiation and absorbing radiation. The balance between what it emits and what it receives from external sources, the sun, other stars, and as we will see, a far older and stranger source, determines its temperature. If more energy arrives than leaves, the object heats up. If more leaves than arrives, it cools down. When the two are equal, the temperature holds steady. There is no surrounding medium to buffer this process. No air to carry excess heat away gradually. No convection to mix warmth and cold into something manageable. The arithmetic of photons in and photons out operates without any moderating influence, and the results can be extreme, more extreme than anything that occurs naturally on Earth's surface. Earth's atmosphere, it turns out, has been silently protecting you from those extremes your entire life, not just by providing air to breathe or pressure to keep your blood from boiling, by acting as a thermal system of extraordinary sophistication, conducting heat through the surface layer, circulating warmth through convection across the entire planet, absorbing and re-emitting radiation in ways that moderate every temperature swing the sun tries to impose. The atmosphere is the reason you have never felt what radiation-only thermal physics actually feels like. Remove it entirely as a thought experiment, and the consequences arrive immediately. The surface facing the sun heats without restraint. The surface in shadow cools without restraint. No convection smooths the boundary between them. No conduction in the thin upper atmosphere bleeds heat from the hot side to the cold. The temperature difference between sunlit and shadowed ground grows until it reaches an equilibrium set by radiation alone. And that equilibrium is hundreds of degrees more violent than anything the atmosphere permits. That is not a thought experiment. It is a description of the moon. And the moon, for reasons we will come to shortly, is one of the most instructive thermometers in the solar system. But before the moon, there is a question worth sitting with for a moment. If radiation is the only mechanism that matters in space, if the thermal state of any object is set entirely by what photons it receives and what photons it emits, then what happens to an object in the deepest, emptiest space of all? Far from any star, far from any galaxy, in a region where no significant local radiation source exists and the object simply floats, emitting its own heat and receiving nothing in return. It cools, slowly, continuously, shedding thermal energy photon by photon into the surrounding void. And it keeps cooling until it reaches a temperature at which it is absorbing exactly as much energy as it emits. A temperature at which it is in thermal equilibrium with its environment. But its environment is not empty. Even in the deepest void, there is something so faint, so uniform, so ancient, that it took humanity most of the 20th century to realize it was there at all. Picture yourself outside the International Space Station, not in a film, not in a simulation, actually outside, 250 miles above the Pacific Ocean, moving at 17,500 miles per hour, tethered to the hull by a single cable, while the Earth fills the lower half of your vision. The sun is out. On the left side of your body, the side facing it, the surface of your suit is absorbing roughly 1,360 watts of solar energy for every square meter of fabric facing the light. That is not a small number. It is approximately the output of a small electric heater pressed flat against every square meter of your sunlit surface, pouring energy in without pause, without the active cooling systems built into your suit. the layers of water-cooled tubing, the carefully engineered thermal management that keeps the interior of the suit at a survivable temperature. The sunlit surface would climb well past 120 degrees Celsius. Hot enough to boil water, hot enough to destroy unprotected electronics, hot enough, given enough time and insufficient insulation, to kill. Now look at the right side of your body, the side facing away from the sun, turned into the shadow behind you. Nothing is coming in from that direction. No solar radiation, no reflected light from the earth below, just the open black of space, and you are radiating. Your suit is constantly emitting infrared photons in every direction, and on the shadowed side, none of those photons are being replaced by incoming energy. The surface is losing heat and gaining nothing. It cools. It keeps cooling. In full shadow, suit surfaces can drop below -170 degrees Celsius, colder than the surface of Mars at its most extreme, cold enough to make rubber brittle and crack, cold enough to freeze lubricants solid and seize mechanisms that were functioning perfectly in the light 30 seconds ago. Think about what that means. On the left side of your body, above 120 degrees. On the right side, below -170. A temperature difference of nearly 300 degrees, measured not across a room or across a city, but across the width of a single human torso. Not because space is one temperature on the left and a different temperature on the right. Space has no temperature in those directions. The void is not doing anything in either direction. What you are experiencing is simply the presence of a powerful radiation source on one side and the absence of any radiation source on the other. And without any atmosphere, any convection, any material medium of any kind to smooth the difference, the boundary between those two thermal environments is not a gradient. It is a cliff. Step from sunlight into shadow in orbit, and the transition does not take minutes or seconds. It is instantaneous at any scale your body can detect. The light stops. The incoming radiation drops to effectively nothing. The surface temperature begins its descent immediately, governed only by how fast the surface can radiate its stored heat away. There is no warm air flowing after you into the shadow. There is no thermal inertia in the surrounding medium. The medium does not exist. The shadow is absolute. This is what spacecraft engineers have grappled with since the first satellites were placed in orbit. A single object moving through low Earth orbit experiences a thermal transition of hundreds of degrees every time it crosses the boundary between sunlight and the shadow of the Earth, roughly once every 45 minutes on a standard orbit. The same object, the same orbit, the same void. But the thermal state of every surface on that object cycles between extremes that would destroy most everyday materials if they were not specifically designed for it. The bolt that holds a solar panel to a structure can be above 100 degrees on its sunlit face, and simultaneously below -150 on its shadowed face. Not over time, at the same moment. Two faces of the same piece of metal, separated by less than a centimeter of thickness, sitting at temperatures that differ by 1/4 of a kilometer on a standard thermometer scale. This is not an engineering edge case. It is the routine thermal reality of every object in orbit, every hour of every day. What this reveals about the nature of cold in space is something the numbers alone do not quite capture. On Earth, cold is an adversary. It presses against you. It finds the gaps in your clothing and exploits them. It follows you into buildings, seeps through walls, strips heat from your skin through the air that surrounds you constantly and inescapably. Cold on Earth is active. It comes after you. The cold of space is nothing like that. It does not come after anything. It simply waits, or rather, it does not even wait, because waiting implies intent. The void is indifferent. It provides no insulation and no source of heat. It offers nothing. If you are receiving radiation, you warm. If you are not, you cool. The universe does not take your heat. It merely stops giving any back. There is no assault. There is only abandonment. That distinction matters more than it might seem. An environment that actively takes your heat is one you can fight directly. Better insulation, more layers, more heat generation. An environment that simply provides nothing is harder to reason about intuitively. The danger is not attack. The danger is the absence of any replenishment. Leave any object in the shadow of space long enough with no internal heat source, and it will cool toward the floor the universe sets. Not because anything is pulling the heat out of it, but because it is emitting radiation and nothing is coming back. The Apollo astronauts who walked on the lunar surface understood this in a way that is difficult to convey through numbers. Moving from sunlight into shadow was not a gradual transition. It was immediate. The shadows cast by rocks, by equipment, by the lunar module itself, were as sharp as shadows in a vacuum can be, which is to say, perfectly sharp, with no atmospheric scattering to soften the edges. Step into one, and the thermal environment changed without warning. Step back into sunlight, and it changed again. The suit managed these transitions through engineering that had to account for both extremes simultaneously, because the astronaut's body was always partly in one and partly in the other. The moon itself makes this physics more visible than anywhere else in the solar system accessible to direct measurement. There is no atmosphere on the moon, not a trace, not a thin wisp of nitrogen, not a scattering of carbon dioxide molecules, nothing. The lunar surface sits in direct contact with the vacuum of space, with no intervening layer of gas to conduct heat across the boundary, no circulation to mix temperatures across regions, no blanket of any kind to moderate what the sun does to the ground and what the darkness does to it in turn. During the lunar day, which lasts approximately 2 weeks at the equator because the moon rotates so slowly, the surface absorbs solar radiation without any atmosphere to reflect or filter it first. The ground heats to approximately 127 degrees Celsius. That is above the boiling point of water. It is hot enough that the early robotic landers had to be specifically engineered to survive it, with careful attention paid to which surfaces faced upward, how heat was managed through the landing legs, and how long the instruments could operate before thermal limits were reached. Then the sun sets. The 2-week lunar night begins. With no atmosphere to retain any of the heat the ground accumulated during the day, the surface radiates its stored thermal energy directly into space. The temperature plummets. By the end of the lunar night, equatorial surface temperatures reach approximately -173 degrees Celsius, a drop of 300 degrees from the daytime peak. The same patch of dust, the same location. 300 degrees of swing driven entirely by the presence or absence of a single radiation source 93 million miles away. Compare that to Earth's most extreme surface environments. In the hottest deserts, the Sahara, the Rub al Khali, the interior of the Australian outback, daytime ground temperatures can reach above 70 degrees Celsius, and nighttime temperatures can drop to near freezing. That is a swing of perhaps 50 to 60 degrees across the most thermally extreme terrain on the planet. The moon's equivalent swing is roughly 5 to 6 times larger. The difference is entirely explained by the atmosphere Earth has, and the moon does not. The air above the desert is absorbing some of the incoming solar radiation before it reaches the ground, reflecting some of it back upward, retaining some of the surface heat after dark through the greenhouse effect, and mixing warm and cool air through convection throughout the day and night. All of these processes working together reduce the thermal swing to something that life can survive. Remove every one of them and you get the moon. The polar craters of the moon push the physics even further. These are regions, some of them kilometers across, where the geometry of the crater walls means the floor never receives direct sunlight. Not just during the lunar night, not during any particular season, ever. Some of these craters have floors that have not been directly illuminated in billions of years. Their angles of inclination too steep, their positions too close to the poles for the sun's rays to reach inside. The Lunar Reconnaissance Orbiter, which has been mapping the moon from orbit since 2009, measured temperatures inside some of these permanently shadowed craters that approach -250 degrees Celsius, placing them among the coldest confirmed locations in the entire solar system. Colder than the surface of Pluto, colder than the moons of Neptune. Cold not because the moon is particularly far from the sun, but because those crater floors have been sitting in perfect shadow. radiating their heat away into space for geological time, with no radiation source of any significance to replenish what they lose. They are, in a very real sense, the closest thing to true deep space cold that exists within reach of our instruments. Not because space itself is cold in those places. The space above those craters is no different from the space above the sunlit lunar plains, but because the surfaces within them have been allowed to equilibrate toward the floor that radiation physics sets, undisturbed, for longer than the entire history of complex life on Earth. That floor is not zero. It cannot be. Something is always arriving, even in the deepest shadow, even in the emptiest void between galaxies. What that something is, where it comes from, what it means, is the next question. And the answer begins at the very moment the universe was born. Before we go back to the beginning of everything, it is worth pausing on what the physics we have just covered has demanded of the engineers who build the machines we send into space. Because the thermal environment of orbit is not an abstract concern. It is one of the primary engineering challenges of every spacecraft ever launched, and the solutions humanity has developed to manage it reveal just how hostile that environment truly is. Every spacecraft in history has faced the same fundamental problem. It must survive both extremes simultaneously, not alternately, not sequentially. At the same moment, different parts of the same structure are fighting overheating on one face and fighting freezing on the other. The engineering response to this problem is one of the most sophisticated and least discussed aspects of space technology. The first line of defense is multi-layer insulation. Look at almost any spacecraft photograph and you will see surfaces wrapped in what appears to be crinkled gold or silver foil. That material is not decorative. It is a carefully engineered thermal blanket. Dozens of alternating layers of highly reflective film, typically aluminized polyester or polyimide, separated by thin spacer layers that prevent direct contact between adjacent sheets. The reflective surfaces bounce incoming solar radiation away before it can be absorbed. The separation between layers creates a series of vacuum gaps that eliminate conduction between them. The result is a blanket that, in the vacuum of space, insulates with extraordinary efficiency, far better than any conventional insulating material could manage in air, because the vacuum between layers removes conduction entirely and forces radiation to do all the thermal work across each gap in sequence. The color and finish of exposed surfaces matter enormously. A spacecraft surface painted white reflects solar radiation efficiently, but also radiates its own heat efficiently, useful for components that generate a lot of internal heat and need to shed it. A surface polished to a metallic finish reflects well, but also retains heat. A black surface absorbs radiation aggressively, but also radiates it away quickly. Every exposed surface on every spacecraft is the color it is, because someone made a deliberate decision about the balance between absorption and emission for that specific component in that specific thermal environment. Nothing is chosen for aesthetics. The International Space Station presents the most complex thermal management challenge of any operational spacecraft in history. The station generates an enormous quantity of heat internally, from the computers running scientific experiments, from the 6 crew members living and working aboard, from the lighting systems, from the power conversion systems that step down solar-generated electricity to usable voltages. All of that energy has nowhere to go except into the structure of the station, and from there into space, the only heat sink available. The solution is the ammonia thermal control system. 2 separate loops of liquid ammonia circulate through the station's structure, collecting heat from internal components and carrying it outward to a set of enormous radiator panels mounted on the station's truss structure. Those panels face permanently away from the sun, presenting their surfaces to the cold void and rejecting heat purely through radiation. Together, the radiator arrays span an area of approximately 2,500 square feet, larger than the playing surface of a basketball court. Without them, the station's internal temperature would rise continuously and without limit, eventually destroying electronics and becoming uninhabitable within hours. At the same time, the station's shadowed components require the opposite treatment. Batteries that spend extended periods in the Earth's shadow during each orbit must be kept above minimum operating temperatures, or their electrochemical processes slow to the point where they cannot deliver power. Fuel lines must not be allowed to freeze. The mechanisms that open and close external hatches, that articulate solar panels, that point antennas, all of them require lubricants that cease to function below certain temperatures. To protect these components, the station carries hundreds of individual electric heaters distributed across its structure, each one drawing power from the solar arrays to maintain the temperature of something that radiation alone would allow to freeze. Flight controllers on the ground in Houston track the thermal state of the station continuously through every one of its 16 daily orbits. It is not a background parameter they check occasionally. It is a primary operational concern, actively managed, with automated systems and human oversight working together to keep every component within its operating range as the station cycles between full solar exposure and the complete darkness of Earth's shadow roughly once every 90 minutes. The history of spaceflight is in part a history of thermal management lessons learned the hard way. The first American satellite, Explorer 1, launched in January of 1958, suffered mysterious telemetry dropouts that were eventually traced to thermal cycling, the antenna electronics overheating in sunlight and cooling past their operating limits in shadow on a timescale the designers had not fully anticipated. Skylab, launched in 1973, lost a critical thermal shield during ascent and nearly had to be abandoned before an extraordinary improvised repair by the first crew saved the station from temperatures that would have made it permanently uninhabitable. Every subsequent program has carried those lessons forward. The Cosmic Background Explorer, the satellite that would later make the most precise measurement of the cosmic temperature floor ever achieved, presented one of the most demanding thermal challenges of any scientific instrument ever built. Its primary detector had to be cooled to below 2 Kelvin, colder than the cosmic background temperature itself, in order to be sensitive enough to measure the faint microwave signal it was designed to detect. The satellite carried a cryogenic system of liquid helium to achieve this, a reservoir that had to be carefully managed across the entire operational life of the mission. The physics of detecting the coldest thing in the universe required building something colder still. That number, 2.7 Kelvin, the temperature the universe defaults to wherever nothing else is happening. Where it came from, and what it tells us about the 13.8 billion years of history encoded in that single measurement, is where this story turns next. The universe did not begin cold. It began as the most extreme thermal event in the history of existence. An event so far beyond any scale of heat or energy that the vocabulary physics uses to describe it starts to feel like a kind of fiction, even though every number in it is real. 13.8 billion years ago, the observable universe, everything you can see through the most powerful telescope ever built, every galaxy, every star, every atom of matter in every direction out to the edge of what light has had time to reach, occupied a volume smaller than a single atomic nucleus, not compressed into a small room, not crushed into a small planet, into a volume smaller than a single atomic nucleus, all of it. At that moment, the temperature was not merely extreme, it exceeded 10 trillion degrees, a number so far outside any thermal reference point in human experience that writing it down does almost nothing to convey what it represents. The core of the sun reaches 15 million degrees. The hottest supernova explosions briefly touch 100 billion degrees. These numbers, staggering in their own right, are separated from the temperature of the first instant by a gap measured in factors of trillions. Here is what matters about that number. The Big Bang was not an explosion that happened inside space, scattering hot material outward into an existing void. It was an explosion of space itself, the expansion of space as a thing, carrying everything within it outward in every direction simultaneously. There was no center. There was no surrounding emptiness waiting to receive the debris. Space came into being, and the heat was everywhere within it, and the expansion of space was already beginning to do what it has never stopped doing, cooling the universe by stretching it. This is the mechanism that connects the fire of the first instant to the 2.7 Kelvin floor measured today. As space expands, the radiation within it is stretched. Wavelengths grow longer. Longer wavelengths carry less energy per photon. Less energy per photon corresponds to lower temperature. The universe is not losing its heat to anything outside itself. There is no outside. It is diluting its heat across an ever-growing volume, spreading the same initial energy across more and more space until the concentration becomes negligibly small. The universe is a machine for converting heat into cold, and it has been running continuously since the first fraction of a second. In the first microsecond, the temperature dropped from its initial extreme to somewhere around 10 trillion degrees, still incomprehensible, but already a fraction of what it had been. By the end of the first second, it had fallen to roughly 10 billion degrees. 10 billion degrees is still hotter than the core of any star that exists in the universe today. Hotter than the interiors of the most massive blue supergiants at their peak of nuclear burning. But it was already, in cosmic terms, a significant cooling from what had existed moments before. The universe at 1 second old was a seething plasma, a dense, uniform fog of protons, neutrons, electrons, photons, and neutrinos, all moving at speeds and energies that would be instantly fatal to any structure more complex than a subatomic particle. Matter and radiation were locked together in a kind of thermal embrace. A photon could not travel more than a microscopic distance before encountering a charged particle and scattering off it in a new direction. The universe was not dark. It was blazing, incandescently, uniformly, impenetrably bright in every direction. But that light was trapped. It could go nowhere. The universe was opaque, not because it lacked light, but because it had so much charged matter that light could not propagate through it at all. This is the opposite of the cold, empty darkness that most people picture when they imagine space. In its first moments, the universe was the most thoroughly filled and most thoroughly energetic environment that has ever existed. What has happened to it in the 13.8 billion years since is entirely a story of cooling, expansion, and the gradual thinning of that original fire into the near-absolute cold that fills the vast majority of space today. There is one more thing worth noting about the thermal conditions of those first moments, something that connects the temperature of the Big Bang to a question that seems unrelated at first. Look at any direction of the sky and measure the temperature of the cosmic microwave background radiation coming from that direction. Now look at the opposite direction and measure again. The temperatures match, not approximately, but to within 1 part in 100,000. The same temperature in every direction, across regions of the sky so distant from each other that at the time the background radiation was released, they had no possible causal connection. Light had not had enough time to travel between them since the Big Bang. How did they come to be at the same temperature? This is called the horizon problem. It is one of the deepest puzzles in cosmology, and it has an answer. An answer involving a period of exponential expansion in the universe's first moments that we will return to in detail. But for now, the problem itself is worth holding on to, because it points to something important. The uniformity of cosmic cold is not accidental. It is the product of physics operating at the very first instant of existence, before anything we would recognize as structure had begun to form. In the first second of the universe, the temperature fell from unimaginable to merely extraordinary. In the next 19 minutes, something remarkable happened. Something that set the chemical composition of the cosmos for all of time that followed, and did so in a window of thermal opportunity so brief that missing it was not a possibility, but a certainty. The window opened when the temperature dropped below roughly 10 billion degrees. At that point, and only at that point, protons and neutrons could begin to bind together without immediately being torn apart by the surrounding radiation. The energy of the photons crashing through the plasma was finally low enough that the strong nuclear force, which holds atomic nuclei together, could win the competition against the photons trying to break those nuclei apart. Nuclear fusion became possible for the first time. What followed is called Big Bang nucleosynthesis. In a period lasting from roughly 1 second after the Big Bang to approximately 20 minutes after it, a span of time comparable to a long lunch break. The universe forged the lightest atomic nuclei from the raw ingredients of the primordial plasma. Single protons remained as hydrogen nuclei, unchanged. Pairs of protons and neutrons fused to form helium-4, the most stable of the light nuclei. Deuterium, a hydrogen nucleus with an added neutron, formed as an intermediate step and survived in small quantities. Helium-3 appeared briefly. Trace amounts of lithium emerged from slightly more complex reactions. And that was essentially the entire inventory. The universe had a nuclear kitchen, and it was open for less than 20 minutes. The proportions locked in during those 20 minutes are precise and measurable. Approximately 75% hydrogen and 25% helium by mass, with trace quantities of deuterium and lithium. These are not rough estimates. They are predictions of the theory of Big Bang nucleosynthesis that can be checked against observation. And every time astronomers measure the composition of the oldest, most chemically pristine stars in the universe, stars that formed before the products of subsequent stellar burning could contaminate the mix, they find the same proportions. The universe began with 3/4 hydrogen and 1/4 helium, and the oldest stars in existence still carry that original signature in their atmospheres. Everything else, every atom of carbon in every living thing, every atom of oxygen in every ocean, every atom of iron in every planet, was not made in the Big Bang. It could not have been. The temperature window required to forge heavier elements opened briefly in the first moments of the universe, then closed before anything heavier than lithium could accumulate in significant quantities. Heavier elements require higher densities and more complex collision sequences than the rapidly expanding and cooling early universe could sustain beyond that brief fusion window. The elements that make chemistry possible, that make planets possible, that make biology possible, had to wait for stars, structures that did not yet exist and would not exist for hundreds of millions of years. By 20 minutes after the Big Bang, the nuclear forge had shut down. The temperature had dropped below 1 billion degrees, still extraordinary, but below the threshold at which the reactions that produce helium from hydrogen could continue. The strong nuclear force could still win individual collisions, but the rate of those collisions had dropped too far as the universe expanded and the plasma thinned. The fusion era was over. Consider the thermal journey already completed. In 20 minutes, the universe had cooled from 10 trillion degrees to below 1 billion. That is a factor of roughly 10 million trillion. A compression of temperature by a number that has no meaningful analogy in ordinary experience. And yet the universe was still extraordinarily hot, still an opaque plasma, still a blazing, uniform, impenetrable fog in which light could not travel freely, and no structure larger than an atomic nucleus had yet formed. The cooling continued. The expansion continued. But the next major transformation, the moment that would release the oldest light in existence and set the thermal baseline still measured today, would not arrive for another 380,000 years. 380,000 years of a universe still too hot, still too dense, still too chaotic for anything we would recognize to exist within it. That long, featureless wait, and the moment it ended, is the next chapter of the story. 380,000 years is a long time by any human measure. It is longer than the entire span of recorded human history by a factor of more than 100. But in the life of the universe, measured against 13.8 billion years, it is barely an opening passage, less than 0.003% of the total time that has elapsed since the Big Bang. And yet those 380,000 years matter enormously, because during all of them, the universe was doing something that would leave its signature in the cold we measure today. After the nuclear forge closed, the universe settled into a state that would persist without dramatic transformation for those hundreds of thousands of years. The plasma era, a period of continuous cooling, continuous expansion, and a kind of cosmic impasse that kept the universe locked in a form it could not escape until the temperature finally fell far enough. The impasse was caused by electrons. After nucleosynthesis, the universe was a plasma, a state of matter in which electrons are not bound to atomic nuclei, but roam freely through the surrounding environment. On Earth, plasmas exist in extreme conditions. Inside lightning bolts, inside the sun, inside the cores of nuclear fusion reactors. They are not common objects in everyday experience. But in the early universe, the plasma state was the only state. The temperature was far too high for electrons to lose enough energy to be captured by a nucleus and form a neutral atom. They had been moving too fast for too long, and the photons filling the plasma were energetic enough to knock any electron straight back out of any atom that tried to form. Free electrons are extraordinarily effective at scattering photons. An electron and a photon interact through electromagnetic force, and when a photon encounters a free electron, it does not pass through. It deflects. It bounces off in a new direction, carrying its energy elsewhere, and immediately encounters another free electron, which deflects it again. In the dense plasma of the early universe, a photon could not travel more than a tiny distance in any direction before being scattered. The mean free path, the average distance a photon could travel before hitting something, was comparable to the size of an atomic nucleus. Light existed everywhere in the universe, in vast and incomprehensible quantities, but it could go nowhere. Every direction was a wall. This is what made the early universe opaque. Not dark, the opposite of dark. It was filled with light in every cubic centimeter of its volume, but that light was imprisoned, ricocheting between free electrons in a random walk that prevented it from carrying information or energy in any coherent direction. If you could somehow have been present inside the early plasma, setting aside the immediate lethality of the conditions, you would not have seen darkness. You would have seen a uniform, featureless, blazing glow in every direction, with no structure visible within it, no depth, no variation. A wall of incandescent fog extending to every horizon simultaneously. As the universe expanded, the plasma cooled. From the tens of millions of degrees remaining after nucleosynthesis, the temperature fell across hundreds of thousands of years toward a critical threshold. The cooling was slow by the standards of what had come before. There were no dramatic nuclear events to punctuate it, no sudden phase transitions, no catastrophic releases of energy, just the steady, relentless dilution of heat across an expanding volume, driving the temperature downward degree by degree toward the point where something would finally change. But while the plasma cooled in this apparently featureless way, something was happening within it that would eventually imprint itself on every cosmological measurement ever made. The plasma was not perfectly smooth. The tiny density variations seeded by quantum fluctuations in the universe's first instance, variations of roughly 1 part in 100,000, meant that some regions were very slightly denser than average, and others were very slightly less dense. In the denser regions, gravity pulled matter inward, but the intense pressure of the trapped radiation pushed outward against it. The competition between gravitational attraction and radiation pressure set the plasma oscillating. These oscillations were sound waves, pressure waves propagating through the photon baryon fluid at roughly 60% of the speed of light. Regions of compression heated slightly and pushed outward. Regions of rarefaction cooled slightly and pulled inward. The waves propagated across vast scales, hundreds of thousands of light years in extent, for the entire duration of the plasma era. Every region of the universe participated in this slow, cosmic drumbeat, a rhythm set by the balance between gravity and radiation, playing out across scales that dwarf anything in the present-day universe. These are called baryon acoustic oscillations. The name sounds technical, but the physical image is straightforward. The universe, before it turned transparent, was ringing like a bell. The sound waves propagated, compressed, rarefied, and oscillated for 380,000 years. And when the moment finally arrived that ended the plasma era and released the imprisoned light, those oscillations were frozen into the pattern of the universe's matter distribution and into the temperature variations of the radiation itself, locked in place at the moment they stopped, preserved across 13.8 billion years of subsequent expansion. The Planck satellite, mapping the cosmic microwave background in extraordinary detail, would eventually read those frozen oscillations and extract from them the proportions of ordinary matter, and dark energy in the universe, the composition of everything, encoded in a temperature variation of 1 part in 100,000, preserved from a moment when the universe was less than 400,000 years old. That moment of preservation, the instant the oscillations froze, the instant the light escaped, the instant the universe turned transparent, was still coming. The temperature had not yet fallen far enough. It needed to reach approximately 3,000 Kelvin, and when it did, everything changed at once. 380,000 years after the Big Bang, the temperature of the universe crossed a threshold below which the entire history of cosmic cold becomes possible. At approximately 3,000 Kelvin, roughly the temperature of a glowing ember or the surface of a dim, ancient star, electrons finally lost enough energy to do something they had been prevented from doing since the first moments of existence. They slowed down enough to be captured. Protons, which had been carrying a positive charge through the plasma since the Big Bang, could finally hold onto electrons against the photon pressure that had been stripping them away for hundreds of thousands of years. A proton reached out, electrostatically speaking, and an electron fell in. A neutral hydrogen atom formed, the first in the history of the universe. Then another, then billions, then trillions. Then the process cascaded through the entire cosmos in a period that was rapid by the standards of what had come before. Helium nuclei, which are more tightly bound and captured their electrons at slightly higher temperatures, had already made the transition moments earlier. But hydrogen, the dominant constituent, completed the shift as the 3,000 Kelvin threshold was crossed. Physicists call this moment recombination. The name is technically misleading. It implies that electrons and nuclei had been combined before and were now rejoining, when in fact this was the first time they had ever been together. But the name has held for decades, and what it describes is one of the most consequential transitions in the history of the universe. The reason it matters so profoundly is what neutral atoms do not do. Neutral atoms, unlike free electrons, do not scatter photons. The electromagnetic interaction that made free electrons into perfect photon deflectors does not operate on neutral matter in the same way. When a photon encounters a neutral hydrogen atom, it passes through without scattering, unless the photon has exactly the right energy to push the atom into an excited state, which the vast majority of CMB photons did not. Effectively, the moment electrons disappeared into atoms, the universe became transparent to radiation. The effect was not gradual. It happened across a cosmological eye blink, a period of perhaps 100,000 years, negligible against the 380,000 that preceded it. One moment, in the language of cosmic time, the universe was an impenetrable fog. The next, it was clear. Every photon that had been trapped, bouncing endlessly through the plasma, carrying the thermal energy of the early universe without ever escaping it, was suddenly free. Released simultaneously across the entire observable universe, those photons streamed outward in straight lines in every direction, carrying with them an image of the universe as it existed at that moment. A nearly uniform, 3,000 Kelvin glow, with tiny temperature variations of 1 part in 100,000 imprinted on it by the density fluctuations and the frozen baryon acoustic oscillations. Those photons have been traveling ever since. 13.8 billion years of uninterrupted flight through an expanding universe, never scattered, never absorbed by anything significant enough to leave a mark on their distribution. They are the oldest light in existence. They are the last light to emerge from the primordial fire, and they are still here, arriving at Earth from every direction, carrying an unbroken message from the moment the universe first became visible. But they do not arrive in the same form they were emitted. This is where the expansion of space does something to radiation that has no everyday parallel. As space stretches, the wavelengths of photons traveling through it are stretched with it. A photon that began its journey as visible light, a wavelength of less than a micrometer, carrying the energy of a 3000 Kelvin photon, has had its wavelength stretched by a factor of roughly 1,000 over 13.8 billion years of cosmic expansion. What was orange-red visible light at the moment of release is now microwave radiation, with a wavelength measured in millimeters and a temperature not of 3000 Kelvin, but of 2.7255 Kelvin. This is why the cosmic background radiation arrives as microwaves rather than light. The universe has not lost those photons. It has simply stretched them beyond the range of any biological eye. The sky still glows in every direction with the light of recombination. You cannot see it, but it is there, filling every cubic centimeter of space, carrying the thermal baseline that every isolated object in the universe will eventually approach if left alone long enough. There remains the question of uniformity. Why does that radiation arrive at the same temperature from every direction in the sky, across regions of the universe that had no causal connection at the time of recombination? Regions separated by distances so great that light had not had time to travel between them since the Big Bang. Regions that should, by any straightforward reasoning, have had no opportunity to reach thermal equilibrium with each other. The answer was worked out in 1981 by a physicist named Alan Guth. His proposal was that the universe, in the first tiny fraction of a second after the Big Bang, far earlier than anything discussed so far, in a period before the plasma era, before nucleosynthesis, before even the first microsecond, underwent a period of exponential expansion so rapid that it staggers any attempt at comprehension. In a span of time, measured in units so small they have no name in ordinary language, a region of space that was small enough to be in complete thermal contact with itself was stretched to scales vastly larger than what would become the observable universe. The regions of the sky that appear causally disconnected at the time of recombination were once in contact. They had equalized their temperatures in the universe's first instance, before inflation tore them apart. The uniformity of the cosmic microwave background is not a coincidence. It is the imprint of a thermal equilibrium achieved before the universe was a microsecond old, preserved across every expansion and every cooling since. The glow left behind by recombination carries all of this, the thermal history of the first 380,000 years, the frozen oscillations of the plasma era, the fingerprint of inflation, the baseline temperature of the cosmos, in a signal so faint that when it was finally detected, the people who found it did not know what they were hearing. In the spring of 1964, two radio astronomers at Bell Telephone Laboratories in Holmdel, New Jersey, were trying to do something straightforward. Arno Penzias and Robert Wilson had been given access to a large horn-shaped antenna, a structure originally built to communicate with the Echo balloon satellites, and they wanted to use it for radio astronomy. Before they could do any serious science with it, they needed to characterize the instrument. They needed to know exactly how much noise it produced on its own, so they could strip that noise out of any future measurements and be confident in what remained. It was careful, unglamorous work, the kind of meticulous calibration that precedes any precision measurement in experimental physics. And it was during this work that they encountered something they could not explain. There was a persistent signal in the data, a faint, uniform hiss corresponding to a thermal source at a temperature of approximately 3.5 Kelvin, barely above absolute zero. It arrived with equal intensity from every direction they pointed the antenna. It did not change with the time of day. It did not vary with the season. It showed no correlation with any known terrestrial radio source, no alignment with the plane of the Milky Way, no variation whatsoever that might indicate a source of finite angular extent. It was simply there, everywhere, equally, always. Penzias and Wilson were not looking for the oldest light in the universe. They were engineers building a scientific instrument, and what they had found looked to them like noise. The question was where it was coming from. They worked through every explanation they could construct. Radio interference from New York City, visible on the horizon from Holmdel, was the first candidate. They checked the directionality of the signal carefully. The hiss did not strengthen toward the city. It was isotropic, the same in every direction. which ruled out any localized terrestrial source. They checked the instrument itself for calibration errors. They recalculated their estimates of the antenna's own thermal emission and found nothing that accounted for the discrepancy. They considered whether the signal might be coming from the residual radioactive fallout from nuclear tests, a real concern in the early 1960s. But the spectrum of the signal was inconsistent with that explanation. Then they noticed the pigeons. A pair of pigeons had been nesting inside the horn of the antenna, and the interior of the structure was coated in what Penzias and Wilson, in the language of the subsequent scientific paper, diplomatically described as a white dielectric material. They removed the pigeons, they cleaned the antenna thoroughly, they reseated the joints in the horn and checked for any physical source of excess thermal noise they might have overlooked. The signal remained, unchanged in intensity, unchanged in direction, unchanged in spectrum. Whatever it was not coming from the pigeons. 40 miles away, at Princeton University, a group of physicists led by Robert Dicke had arrived at a completely different starting point and were converging on the same target from the opposite direction. Dicke, working with a young theorist named Jim Peebles, had been thinking carefully about the Big Bang model of the universe. Peebles had calculated that if the universe had indeed begun in a hot, dense state, the cooling of that initial fireball should have left behind a faint thermal radiation field permeating all of space, a relic glow at a temperature of a few Kelvin, arriving from every direction. It was a prediction that followed directly from the physics of the early universe, and the Princeton group had already begun designing a radiometer to search for it. They had not yet searched. They were still building the instrument when the phone call came. A mutual colleague connected the two groups, and when Penzias called Dicke to describe the anomalous signal he and Wilson had been unable to explain, Dicke listened and then turned to his colleagues in the room. His words, as they were later recalled, were brief. They had been scooped. What Penzias and Wilson had found while trying to eliminate noise was the cosmic microwave background radiation, the thermal afterglow of the Big Bang itself. The signal that the Princeton group had predicted and were preparing to search for had already been sitting in a Bell Laboratories dataset for months, unrecognized, catalogued as an instrumental nuisance. The two groups published simultaneously in 1965, in adjacent papers in the Astrophysical Journal. Penzias and Wilson described the observation, a measurement of excess antenna temperature at a fixed intensity, in careful, restrained language that gave almost no indication of what the signal represented. The Princeton paper, by Dicke, Peebles, Roll, and Wilkinson, provided the cosmological interpretation. Together, the two papers constituted one of the most significant observational discoveries in the history of science. In 1978, Penzias and Wilson were awarded the Nobel Prize in Physics for the detection of the cosmic microwave background. Dicke and Peebles, who had provided the theoretical framework that gave the detection its meaning, were not included. It is one of the more discussed asymmetries in the history of Nobel Awards, though Peebles would eventually receive his own Nobel Prize in Physics in 2019 for theoretical cosmology, recognition that arrived more than half a century after the work that had first pointed toward the discovery. What the detection meant was not immediately absorbed by the scientific community or by the public. But in the years that followed, as the implications were worked through, it became clear that Penzias and Wilson had done something without intending to. They had detected the oldest light in the universe. They had found the moment the universe became transparent. They had reached back 13.8 billion years with a radio antenna in New Jersey and touched the surface of last scattering. And the measurement of the temperature of that light, the precision pinning of 2.7 Kelvin as the thermal baseline of the entire cosmos, was still to come. The detection by Penzias and Wilson had established that the cosmic microwave background existed. It had not measured it with any precision. The original reading of approximately 3.5 Kelvin carried significant uncertainty, and the instrument that produced it had never been designed for cosmological measurements. It was a beginning, not an answer. Pinning the temperature of the cosmic background to the precision the science required demanded something that ground-based instruments could not provide. The problem was the atmosphere. Earth's atmosphere absorbs microwave radiation. It also emits it. Any telescope or antenna sitting beneath the atmosphere is trying to detect a faint cosmic signal, while the atmosphere is simultaneously generating its own microwave noise in every frequency range of interest. Ground-based observers could subtract this contamination approximately, but only approximately. The uncertainties introduced by atmospheric emission set a fundamental limit on how precisely any ground-based instrument could measure the CMB temperature. To do better, you had to get above the atmosphere entirely. In November of 1989, NASA launched the Cosmic Background Explorer, COBE, into a near-polar orbit 570 kilometers above Earth. It was the first satellite dedicated specifically to measuring the cosmic microwave background from above the atmosphere, and it carried two instruments that would each produce a Nobel Prize-worthy result. The first was the Far-Infrared Absolute Spectrophotometer, built under the scientific leadership of John Mather at NASA Goddard Space Flight Center. Its purpose was to measure the precise spectrum of the CMB, to determine exactly how the intensity of the radiation varied across wavelengths and compare it against theoretical predictions. The prediction was specific. If the CMB was truly thermal radiation from a hot, dense, uniform early universe, its spectrum should follow the mathematical form of a perfect blackbody radiator with extraordinary precision. The result, when Mather presented it at a meeting of the American Astronomical Society in January of 1990, produced a standing ovation from the assembled scientists, a response essentially without precedent in the history of scientific conference presentations. The data points fell on the theoretical blackbody curve so precisely that when plotted, the error bars were smaller than the thickness of the line itself. The spectrum was the most perfect blackbody ever measured in nature, confirming beyond any remaining doubt that the CMB was thermal radiation from the early universe and pinning the temperature to 2.725 Kelvin. The second instrument was the Differential Microwave Radiometer, built under the scientific leadership of George Smoot at the University of California, Berkeley. Where FIRUS measured the spectrum of the CMB with precision, the DMR mapped its temperature across the full sky, looking for variations. The prediction was that tiny temperature fluctuations should exist, the imprint of the primordial density variations that seeded all cosmic structure, but they were expected to be extraordinarily small. Detecting them at all was considered a formidable observational challenge. In 1992, Smoot announced that the DMR had found them. Temperature fluctuations of roughly 1 part in 100,000, variations of about 30 millionths of a degree against the 2.7 Kelvin average, were present in the CMB map at a level consistent with the theoretical predictions of structure formation. Regions that were slightly warmer at the time of recombination corresponded to regions of slightly higher density. Regions where gravity would eventually draw matter together into the filaments and clusters that became the large-scale structure of the universe. The temperature map of the CMB was a map of the seeds of everything. In 2006, Mather and Smoot were jointly awarded the Nobel Prize in Physics for their work on COBE. The next step was resolution. COBE had mapped the CMB temperature fluctuations, but its angular resolution was limited. It could distinguish features no smaller than about 7 degrees across the sky, roughly 14 times the diameter of the full moon. The acoustic peaks imprinted by baryon acoustic oscillations in the plasma era required far finer resolution to map. A successor instrument was needed. The Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001 and took up position at the second Lagrange point of the Earth-Sun system, 1.5 million kilometers from Earth on the night side, where it could observe the sky without interference from Earth's thermal emission. WMAP had roughly 35 times the angular resolution of COBE and mapped the full CMB sky in 5 frequency bands over 9 years of operation. Its data established the age of the universe at 13.77 billion years, measured ordinary matter at 4.6% of the total energy content, dark matter at approximately 23%, and dark energy, the mysterious force accelerating the expansion of the universe, at approximately 72%. These proportions, extracted from temperature variations of millionths of a degree in ancient microwave radiation, formed the quantitative foundation of modern cosmology. The definitive measurement came from the Planck satellite, launched by the European Space Agency in 2009. Planck observed the CMB in 9 frequency bands with angular resolution and sensitivity that surpassed WMAP by a further significant margin. Its maps of the temperature fluctuations revealed the acoustic peak structure in extraordinary detail, constraining models of inflation and measuring the composition of the universe with percent-level precision. Planck established the age of the universe at 13.798 billion years and confirmed the CMB temperature at 2.7255 Kelvin. Dale Fixon at NASA Goddard, who had spent years consolidating every precise measurement of the CMB temperature ever made, arrived at an agreed value of 2.7255 Kelvin with an uncertainty of less than 1,000th of a degree. This is the number, the thermal baseline of the universe, the temperature that every isolated object in the deepest void will eventually approach. A fossil of creation, measured with the precision of a laboratory instrument, encoding in a single number the entire thermal history of the cosmos from its first moments to today. 2.7255 Kelvin. A number that cold and a story that large. But the story of cosmic cold does not begin with the CMB, and it does not end with it. After recombination, after the light escaped, the universe entered a period of darkness unlike anything before or since. And what came out of that darkness is what made the thermal landscape we now inhabit possible. The cosmic dark ages is not a metaphor. It is a literal description of the state of the universe in the hundreds of millions of years that followed recombination, a period during which no star burned anywhere, no galaxy shone, and the universe produced no light of its own at all. After the CMB photons were released and streamed away from the surface of last scattering, the universe was left as a cooling, neutral fog of hydrogen and helium gas. The matter that remained after recombination was electrically neutral, chemically simple, and structurally almost featureless. The tiny density variations seeded by quantum fluctuations in the first moments, those 1 part in 100,000 variations preserved in the CMB temperature map, were present, but they were not yet structures. They were tendencies. Regions that were very slightly denser than average had very slightly stronger gravitational pull, and over time that marginal advantage would compound. But in the early dark ages, the compounding had barely begun. The temperature continued to fall. In the immediate aftermath of recombination, the universe was at roughly 3,000 Kelvin, warm enough to glow deep red if you could somehow see it. But the expansion of space continued, diluting the thermal energy of the gas as it stretched the volume within which that gas was contained. Hundreds of Kelvin became tens of Kelvin. Tens of Kelvin became single digits. The gas grew cold and dark and quiet. No nuclear reactions heated it. No radiation sources warmed it. The CMB photons that filled the universe were fading from infrared toward microwave as their wavelengths were stretched. And as they faded, they carried less and less energy to the gas they passed through. For perhaps 200 million years, some estimates reach as high as 370 million. The universe was in this state, dark, cold, structureless to any casual observer, though the seeds of everything were quietly amplifying beneath the surface. It is the least understood era in the history of the cosmos, precisely because it produced no light that any telescope can directly detect. It is reconstructed from theory and inference rather than observation, and its details remain genuinely uncertain. What broke the Dark Ages was gravity. In the regions of slightly elevated density, gas was slowly accumulating. Dark matter, which interacts gravitationally but not electromagnetically, and had therefore been free to begin clustering even before recombination, had already begun drawing ordinary matter toward the denser nodes of what would become the cosmic web. As gas fell into these gravitational wells, it compressed. As it compressed, it heated. And as it heated, it reached a threshold. The first stars ignited somewhere in that dark, cold universe, probably somewhere between 150 million and 250 million years after the Big Bang. Cosmologists call them population 3 stars, and they were unlike anything that exists in the universe today. The reason for their extreme nature lies in their composition. Every star that burns in the modern universe formed from gas that had already been processed through at least one previous generation of stellar burning. Gas enriched with carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements heavier than helium, collectively called metals by astronomers. These heavy elements play a critical role in star formation. They are efficient radiators. When a cloud of gas collapses under gravity, it heats up as it compresses, and that heating creates pressure that resists further collapse. In a metal-enriched cloud, heavy elements radiate away that thermal energy quickly, allowing the cloud to cool and continue collapsing at lower masses. The presence of metals acts as a brake on temperature, allowing stellar nurseries to fragment into the relatively modest stellar masses typical of stars today. The gas from which population 3 stars formed contained none of this. It was pure primordial material, 75% hydrogen and 25% helium, with trace lithium. No heavy elements at all. Without metals to radiate away thermal energy during collapse, the gas cloud had to reach far higher temperatures before the outward pressure it generated could be overcome by gravity. The collapse had to go further. The mass that accumulated before fusion ignited was consequently far greater. Researchers including Volker Braun at the University of Texas and Richard Larson at Yale, working on the theory of primordial star formation, calculated that population 3 stars likely reached masses of 100 to several hundred times the mass of the Sun, perhaps more. Their surface temperatures would have dwarfed those of the hottest stars burning today. Their luminosities were extraordinary, and their lifespans were brief, a few million years at most, before they burned through their fuel and died in explosions of tremendous violence. But before they died, they did something that changed the universe permanently. They flooded the surrounding neutral hydrogen gas with ultraviolet radiation. Ultraviolet photons carry enough energy to strip electrons from hydrogen atoms, to ionize them. As the first population 3 stars began pouring ultraviolet light into the surrounding dark ages, bubbles of ionized hydrogen grew around them, expanding outward and eventually merging with the bubbles from neighboring stars. The neutral hydrogen of the dark ages began to disappear, replaced by ionized plasma once more. The universe became transparent to visible light again for the first time since before recombination. Astronomers call this the epoch of reionization. The James Webb Space Telescope, operating at the frontier of observational astronomy, has begun detecting some of the earliest galaxies ever observed, objects whose light has been traveling for more than 13 billion years, pushing back toward the epoch when the first stars were igniting and reionization was beginning. The 21-centimeter hydrogen line, the radio emission characteristic of neutral hydrogen gas, offers another avenue for probing the dark ages directly, and the square-kilometer array, the largest radio telescope ever constructed, is expected to map the epoch of reionization in detail once fully operational. The first fire that ended the Dark Ages also seeded the cosmos with the heavy elements that everything in the modern universe is built from. Every population 3 star that exploded scattered newly forged carbon, oxygen, and heavier elements into the surrounding gas. The next generation of stars formed from this enriched material, and the generation after that, richer still. Every atom of iron in every planet, every atom of carbon in every living cell, traces its origin through this chain of stellar burning that began in the dark. The universe that emerged from the Dark Ages was not the universe we inhabit today. It was younger, hotter in its active regions, and structurally simpler. But it was recognizably the beginning of what we have now. And what we have now, in terms of its thermal structure, is something more complex and more varied than any simple description of cold space can capture. Step back from the largest scales of the cosmos for a moment and look at the Milky Way alone, a single galaxy. one structure among an estimated 2 trillion in the observable universe. What you find when you look carefully at the space between its stars is not a single thermal environment, but 5 distinct ones, each defined by different physical processes, each coexisting across the galaxy simultaneously. The coldest are the molecular clouds, dense concentrations of gas and dust where hydrogen exists in molecular form, paired atoms rather than single ones, at temperatures between 10 and 30 Kelvin, barely above the cosmic background. In some of the densest cores, temperatures drop as low as 8 or 10 Kelvin. These are, in the present-day universe, the coldest naturally occurring environments that exist. Not in the deep void between galaxies, not in the permanently shadowed craters of the Moon. Inside galaxies, inside the dense structures that form within them, in the hearts of the molecular clouds, where the next generation of stars is preparing to ignite. Above the molecular clouds in temperature, but still cold by any human standard, is the cold, neutral medium, atomic hydrogen at temperatures between 50 and 100 Kelvin, spread more diffusely through the galactic disk. Too cold to emit visible light, it reveals itself through the 21-centimeter radio emission line, a characteristic signature of neutral hydrogen that radio telescopes have been mapping across the galaxy for decades. Warmer still is the warm neutral medium, atomic hydrogen at 6,000 to 10,000 Kelvin, heated by the general radiation field of the galaxy, but not yet ionized. This phase fills a substantial fraction of the galactic volume. Above it sits the warm, ionized medium, at similar temperatures, but with hydrogen already stripped of its electrons by ultraviolet radiation from nearby hot young stars. The glowing material of emission nebulae, visible in photographs as the luminous clouds surrounding star-forming regions. And threading through all of this, filling the spaces between denser structures with an almost invisible presence, is the hot ionized medium, gas heated to temperatures between 100,000 and several million Kelvin by the blast waves of supernova explosions. By the intensive measure of particle velocity, it is among the hottest material in the galaxy. But as established earlier, temperature and thermal energy are not the same thing. The hot ionized medium is so vanishingly sparse, typically less than 1 particle per 100 cubic centimeters, that it carries almost no thermal energy at all. Christopher McKee at the University of California, Berkeley, and Jeremiah Ostriker at Princeton developed the foundational model for understanding how these phases coexist and interact, recognizing in the 1970s that supernova explosions are the primary engine that maintains the hot ionized medium and regulates the thermal structure of the galaxy as a whole. Their framework remains the basis of how astronomers understand galactic thermal physics today. Here is the paradox that the 5-phase structure makes vivid. The coldest places in the galaxy, the molecular clouds at 10 Kelvin, barely warmer than the cosmic background, are precisely where the hottest objects are being created. Stars do not form in the warm regions or the hot regions. They form where the gas is cold enough to collapse, dense enough to accumulate mass, and quiet enough for gravity to win against thermal pressure. The cold is not the absence of stellar fire, it is its prerequisite. Every star that has ever burned in the Milky Way was born in the cold. A galaxy, seen honestly, is not a warm place. It is a collection of thermal extremes embedded in a matrix that is, by volume, almost entirely cold. And the cold is not incidental to what the galaxy does. It is essential to it. All of this, the 5 thermal phases of the interstellar medium, the molecular clouds at 10 Kelvin, the hot ionized gas at millions of degrees, the paradox of cold as the birthplace of stellar fire, describes the structure within a single galaxy. But to understand what the universe is actually made of, thermally speaking, you need to step back further and look at the full inventory of hot things. The stars, the supernova, the accretion disks, the genuine thermal exceptions. Because they are real, they are spectacular, and they are the reason this topic feels so counterintuitive to anyone who has ever stood under a clear night sky and looked up at a universe that appears, from that vantage point, to be full of light. The sun, at the scale of human experience, is overwhelming. Its radiation drives weather, powers biology, determines the habitability of an entire planet. Its surface burns at approximately 5,500 degrees Celsius. Its core, where hydrogen is crushed into helium by the weight of the overlying mass, reaches 15 million degrees, sustaining the fusion reactions that have been running for 4.5 billion years and will continue for approximately 5 billion more. These are numbers that dwarf any thermal process on Earth's surface by factors of thousands. But the sun, it must be said clearly, is unremarkable among stars. It is a middle-aged, middle-mass yellow dwarf, sitting in the outer reaches of an average spiral galaxy. It neither burns the hottest nor lives the longest. It is simply the star that happens to be close enough to matter to us. At the hotter end of the stellar spectrum, blue supergiants like Rigel, visible in the constellation of Orion as one of the brightest stars in the night sky, burn at surface temperatures exceeding 11,000 degrees Celsius, roughly twice the temperature of the sun's photosphere. Inside, their cores reach hundreds of millions of degrees, fusing not just hydrogen, but helium, carbon, oxygen, neon, and progressively heavier elements in nested shells of nuclear fire, each shell burning at a higher temperature than the last. These stars are engines of staggering power, radiating tens of thousands of times more energy per second than the sun. Their price for burning so extravagantly is brevity. A star like Rigel will exhaust its fuel in a few million years, less than 0.1% of the sun's expected lifespan. At the opposite end, red dwarfs burn with a patience that is difficult to properly appreciate. With surface temperatures around 3,000 degrees Celsius and masses between roughly 8 and 50% of the sun's, they radiate so little energy that not a single red dwarf is visible to the naked eye from Earth. They are dim, cool, and extraordinarily long-lived. The least massive red dwarfs will burn steadily for 10 trillion years or more, roughly 1,000 times the current age of the universe. And because they are by far the most numerous stellar type, comprising roughly 70% of all stars in the Milky Way, they will be the last fires burning in the universe long after every other type of star has gone dark. Not a single red dwarf in the history of the cosmos has yet exhausted its fuel. Every one that has ever ignited is still burning today. Beyond the stars, the thermal environments around black holes represent some of the most extreme temperatures in the modern universe. When matter falls toward a black hole, it does not fall in cleanly. It accumulates in an accretion disk, a swirling structure of gas and dust compressed by gravitational tidal forces as it spirals inward. In the innermost regions of the disk, the compression is so intense and the velocity so high that friction heats the material to temperatures far exceeding anything achievable in stellar interiors. Around stellar mass black holes, objects with masses of 10 to perhaps 100 times the sun, the inner accretion disk reaches tens of millions of degrees. Around the supermassive black holes at the centers of galaxies, with masses of millions or billions of solar masses, the temperatures climb further still, hundreds of millions to 1 billion degrees or more in the most luminous active galactic nuclei. These are among the highest sustained temperatures anywhere in the present-day universe, produced not by nuclear fusion, but by the conversion of gravitational potential energy into heat, as matter falls toward an object so dense that not even light can escape its interior. Jenny Green at Princeton has worked extensively on the thermal environments of black holes across the mass spectrum, including the intermediate mass black holes, whose accretion structures occupy the thermal range between their stellar and supermassive counterparts. The full thermal landscape of accreting systems spans many orders of magnitude in temperature, all of it driven by the same fundamental physics: gravity pulling matter inward, orbital mechanics converting gravitational energy into heat. And then there are supernovae. When a massive star exhausts the fuel in its iron core, the endpoint of the nested fusion shells, at which point no further energy can be extracted by fusion because iron is the most tightly bound of all atomic nuclei, the core collapses. In less than a second, a sphere of matter with the mass of the sun implodes from the size of Earth to the size of a city. The densities reached in that implosion are so extreme that the infalling material bounces off the incompressible nuclear matter of the protoneutron star and sends a shockwave outward through the stellar envelope with an energy release that briefly rivals the luminous output of an entire galaxy. In the collapsed core, temperatures reach approximately 100 billion degrees, hotter than the universe has been at any point since its first second of existence. For an instant, in a dying star, the thermal conditions of the Big Bang are recreated. Then the star explodes outward and the heat disperses. The remnant expands for thousands of years, cooling as it goes, eventually merging with the surrounding interstellar medium. The thermal violence was real and spectacular, but it was brief. A match struck in a dark room illuminates everything for a moment, then the darkness returns. All of these thermal objects are real. The Sun's 15 million degree core is real. Rigel's surface temperature is real. The billion-degree accretion disk around a quasar is real. The 100 billion degree supernova core collapse is real. They are not hypothetical, not exaggerated, not in any sense diminished by what comes next. What comes next is a question of proportion, and it is here that the intuition built from a lifetime of looking at a sky full of stars collides with a calculation that is genuinely difficult to absorb. The observable universe has a radius of approximately 46.5 billion light-years. Its total volume is a number so large that expressing it requires scientific notation. Approximately 4.2 times 10 to the power of 80 cubic meters. Within that volume, there are an estimated 10 to the power of 24 stars. Each star has a volume. The Sun's volume is approximately 1.4 times 10 to the power of 27 cubic meters. Taking the sum of all stellar volumes, accounting for the fact that most stars are smaller than the Sun, and dividing by the total volume of the observable universe yields a fraction on the order of 10 to the power of minus 29. Read that number again. 10 to the power of minus 29. That is a decimal point followed by 28 zeros, and then a 1. Stellar interiors, the only places in the universe where nuclear fusion actively generates new thermal energy, occupy less than 1/1000th of 1/1000th of 1/1000th of the total volume of space. Think about what that means for the image of space as a place full of light and heat. Every star you have ever seen in the night sky, every galaxy photographed by every telescope ever pointed at the heavens, the entirety of the luminous universe, all of it fits into a fraction of cosmic volume so small that rounding it to zero would introduce an error smaller than the uncertainty in almost any other cosmological measurement. The universe is not full of stars. The universe contains stars, the way the ocean contains islands, as scattered exceptions in an overwhelming and dominant emptiness. The habitable zone around a star, the orbital band where temperatures permit liquid water on a rocky planetary surface, is a further reduction of an already negligible volume. Our own habitable zone spans a band of roughly 150 million kilometers in width around the Sun. Measured against the 4 light-years of empty space separating the Sun from its nearest neighbor, that band occupies an infinitesimal sliver. Measured against the total volume of the observable universe, it is not a sliver at all. It is, quite literally, nothing, a fraction so small that no useful analogy conveys it. The inverse square law ensures that stellar radiation becomes negligible with distance far more rapidly than most people intuitively appreciate. Double the distance from a star and the intensity of its radiation drops to 1/4. Triple it and the intensity drops to 1/9. At 4 light-years from any star, the typical distance between neighboring stars in our part of the galaxy, the radiation from that star is reduced to such a faint trickle that a rogue planet floating in interstellar space at that distance would receive less energy from the nearest sun than it radiates away through its own thermal emission. It would cool, continuously, toward the floor. Then there is the intergalactic medium, the gas that fills the vast spaces between galaxies. In the filaments of the cosmic web, this material exists in a phase called the warm-hot intergalactic medium at temperatures between 100,000 and 10 million Kelvin. By the formal definition, it is hot, but the density is so extraordinarily low, perhaps 1 particle per cubic meter or less, that its thermal energy content per unit volume is negligible. Pass through 1 million light-years of this material and you would gain no perceptible warmth. High temperature, near zero thermal energy. The lesson from Chapter 2 comes back. Temperature and warmth are not the same thing when the matter is sparse enough. The universe contains hot things. It is not a hot universe. The cold does not compete with the warmth. It does not need to. It simply occupies all the volume that the hot things do not, which is essentially all of the volume there is. This is not a poetic observation. It is an arithmetic one. The numbers have been done. The fraction has been calculated. And when you hold the result in your mind alongside the image of a sky full of stars, you are holding two things that are both true and that most people have never put together at the same time. The stars are real. The cold is more real. It is everywhere the stars are not. And the stars are almost nowhere. To see just how completely the cold dominates, you need to look at the universe at its largest scales, not at the level of individual stars or even individual galaxies, but at the structure of the cosmos as a whole. And at that scale, what you find is a picture that makes the 10 to the power of minus 29 stellar volume fraction look almost generous by comparison. The universe is not a uniform distribution of matter. Galaxies are not scattered randomly through space like raisins in a cake. They are organized, drawn by gravity over billions of years into a vast, interconnected architecture called the cosmic web. Thin filaments of galaxies stretch across hundreds of millions of light years. Where multiple filaments intersect, they form dense knots called galaxy clusters. Concentrations of thousands of galaxies bound together by gravity, surrounded by superheated gas that glows in X-ray light. Between the filaments and clusters, sheets of more diffuse galaxies trace out the walls of an enormous cellular structure. The Sloan Digital Sky Survey produced the most detailed three-dimensional maps of this structure ever assembled, charting the positions of hundreds of millions of galaxies across a significant fraction of the observable universe. The maps that emerged from that data are striking not for what they show, but for what they do not. The dominant feature of the cosmic web is not the galaxies. It is the emptiness between them, the voids. Cosmic voids are regions of the universe that contain almost no galaxies, vast three-dimensional spaces where the density of matter drops far below the cosmic average. They are not rare. They are not edge cases or curiosities. They are the dominant structural feature of the universe by volume, occupying an estimated 80 to 90% of the total volume of the observable cosmos. The filaments and walls and clusters that contain almost all the galaxies, and almost all the stars, and almost all the light are crammed into the remaining 10 to 20%. The Botas void, identified in the 1980s, was one of the first supervoids to enter the scientific literature and to prompt serious questions about whether it could exist within the standard framework of cosmological structure formation. It spans approximately 330 million light-years in diameter and contains fewer than 60 known galaxies in its interior. Our own local group, the collection of galaxies that includes the Milky Way and Andromeda, contains more than 50 galaxies packed into a region roughly 10 million light-years across. The Botas void is 33 times wider and holds roughly the same number. If our galaxy sat at the center of the Botas void rather than within the local group, the nearest external galaxy would be enormously further away than it actually is. The night sky, stripped of the Milky Way's own stars, would be nearly dark. The KBC void, named for the researchers who characterized it, is a candidate for one of the largest underdensities yet identified in the observable universe, potentially spanning roughly 2 billion light-years. Its existence and precise boundaries remain a subject of active research, and its possible relationship to the Hubble tension, the ongoing discrepancy between different measurements of the universe's expansion rate, has made it a focus of significant attention in recent cosmology. The CMB itself contains an anomaly that may be related to a void structure. There is a region of the cosmic microwave background, visible in the maps produced by WMAP and Planck, where the temperature is anomalously low, a cold spot that sits well outside what would be expected from the standard statistical distribution of CMB temperature fluctuations. Lawrence Rudnick at the University of Minnesota identified a candidate supervoid along the line of sight to this cold spot, proposing that the underdensity was producing a measurable cooling effect on CMB photons passing through it, photons losing energy as they climbed out of the gravitational potential well of the void. Whether the supervoid fully accounts for the anomaly, or whether it represents something more unusual, remains genuinely unresolved. Inside a void, the thermal environment approaches the purest expression of cosmic cold that exists anywhere in the present-day universe. With almost no galaxies nearby, almost no stars, almost no radiation sources of any significance, the temperature of any object left alone in a void will equilibrate toward the CMB baseline. 2.7 Kelvin. No stellar radiation to complicate the calculation. No heated interstellar gas to contribute even a negligible warmth. Just the ancient microwave glow of recombination, fading slowly as the universe expands, cooling by fractions of a degree per billion years. The voids are the universe's default. They are what most of space is, and they will not warm up. There is no mechanism that will fill them with stars. The matter that might have formed galaxies and stellar populations within them was drawn away by the gravity of the denser surrounding regions billions of years ago. What remains will remain, cold, dark, and growing colder and darker as the expansion of space pushes the surrounding filaments further away. Now extend the timeline. The universe we inhabit is often described as if it were in its prime, and in a narrow sense it is, because stars are still forming and burning in large numbers, and the products of stellar nucleosynthesis are still enriching the interstellar medium with the heavy elements that make rocky planets and biological chemistry possible. But the arc of stellar history is not flat. It has a peak, and that peak is behind us. The rate of star formation across the universe reached its maximum approximately 10 billion years ago in the period cosmologists call cosmic noon. Since then, it has been declining. The universe is using up its reserves of cold, dense gas, the molecular clouds that collapse to form stars, faster than those reserves are being replenished. The star formation rate today is roughly 10 times lower than it was at its peak. The universe, in terms of stellar production, is already in a slow decline that will continue until the last molecular cloud collapses and the last new star ignites. Cosmologists call the current era the Stelliferous Era, the Age of Stars. It extends from the first stellar ignition several hundred million years after the Big Bang through to the exhaustion of all star-forming material, a point estimated to lie roughly 100 trillion years in the future. 100 trillion years sounds like an eternity. What follows makes it look brief. Freeman Dyson, working at the Institute for Advanced Study in Princeton, published a paper in 1979 that was one of the first serious physical treatments of the universe on timescales beyond the stellar era. What followed from Dyson's work, and what was later developed in comprehensive detail by Fred Adams at the University of Michigan and Gregory Laughlin at Yale, was a picture of the universe's future divided into eras, defined by what dominates the cosmos and what physical processes remain available. After the last stars exhaust their fuel, the degenerate era begins. The universe will be populated not by burning stars, but by their cooling remnants, white dwarfs, neutron stars, and the brown dwarfs that never quite achieved ignition. These objects retain residual heat from their formation and previous burning, but they produce no new energy. They simply radiate what they have into the surrounding void, growing cooler across timescales measured in quadrillions of years. White dwarfs will fade from brilliant white through yellow, orange, red, and finally infrared, approaching the CMB baseline as they exhaust their stored thermal energy. Each one is a miniature reenactment of the universe's own thermal history, born hot, cooling slowly, approaching, but never quite reaching absolute cold. Following the degenerate era, Stephen Hawking's 1974 prediction of black hole evaporation defines what comes next. Hawking showed that black holes are not permanent. Quantum mechanical effects at the event horizon cause them to emit radiation and slowly lose mass. The process is extraordinarily slow. A stellar mass black hole with a mass of perhaps 10 times the Sun requires approximately 10 to the power of 67 years to evaporate completely. A supermassive black hole at the center of a large galaxy with a mass of billions of solar masses requires approximately 10 to the power of 100 years. To absorb the scale of those numbers, the entire current age of the universe is approximately 10 to the power of 10 years. The time required for a supermassive black hole to evaporate is 10 to the power of 100 years, a number so incomparably larger than the current age of the universe that placing them side by side in words does almost nothing to convey the difference. The entire stelliferous era, from the first star to the last, spans roughly 10 to the power of 14 years. In the timeline defined by black hole evaporation, the age of stars is not even a rounding error. It is a rounding error's rounding error. After the last black hole evaporates, the dark era begins. A universe of diffuse photons and the lightest subatomic particles, expanding into infinite cold silence, with temperatures approaching but never quite reaching absolute zero. No structures, no processes that generate heat, no light. The expansion of space continuing endlessly, stretching whatever remains further apart with every passing moment, until even the concept of distance loses the meaning it carries today. Here is the image that makes the scale of all of this legible. Imagine the full future history of the universe, from now, through the end of the stelliferous era, through the degenerate era, through the entire black hole era, to the evaporation of the last supermassive black hole, compressed into a single year. January the 1st is now. December the 31st is the end. The entire age of stars. 100 trillion years of stellar burning, of supernovae, of planetary systems, of everything that has ever happened under the light of a sun, would occupy a fraction of a millisecond after midnight on January the 1st. The rest of the year, every month, every week, every hour, every second of every remaining day until the final moment of December passes in darkness and cold. The warmth is not a dominant feature of the universe's history. It is a brief opening passage, already more than half complete, in a story whose overwhelming bulk is written in cold. Pull back from the timeline, come back to the present. To a universe that is 13.8 billion years into its story, a fraction of the way through a future so long that the whole of history from the Big Bang to now is a barely detectable opening movement. Here is what that story adds up to. The universe was born in fire. It cooled continuously from a temperature that had no analog, shedding heat across billions of years, stretching its own radiation until the primordial blaze became a 2.7 Kelvin whisper, filling every cubic centimeter of space. It is dominated by cold across 80 to 90% of its volume. Its hot objects, every star, every accretion disk, every glowing nebula, occupy a fraction of total volume so small that expressing it requires a negative exponent of 29. It is already past the peak of its star formation. It is already in the long, slow decline toward a darkness from which there will be no return. And in the middle of all of this, on a rocky planet orbiting an unremarkable star in the outer reaches of one galaxy among 2 trillion, there is warmth. Not accidental warmth, not simple warmth. Warmth that required the right star burning at the right rate, the right orbital distance maintained over 4.5 billion years, the right planetary mass to hold an atmosphere against the constant pressure of the solar wind, the right magnetic field generated by the right kind of molten iron core rotating in the right way to deflect the charged particles that would otherwise strip that atmosphere away. Warmth that required the carbonate-silicate cycle, a geological thermostat operating across 100 million year timescales to regulate carbon dioxide in the atmosphere well enough to prevent the oceans from boiling or freezing permanently. Warmth that required water, Delivered in the right quantity by the right combination of comets and asteroids, during a violent early period, the planet barely survived. A moon large enough to stabilize the axial tilt. A giant planet in the outer system deflecting some of the bombardment that would otherwise have sterilized the inner planets repeatedly. Pull any single thread from that chain and the warmth likely disappears. The search for warmth elsewhere is the search for another chain like this one, equally complete, equally improbable, equally sustained. The James Webb Space Telescope is currently examining the atmospheres of planets orbiting nearby stars, looking for chemical signatures that might indicate conditions compatible with liquid water. The 7 rocky worlds of the TRAPPIST-1 system, orbiting a red dwarf star roughly 40 light-years from Earth, are among the most closely watched candidates. Some of them orbit within the habitable zone. Whether any of them are genuinely warm in the way that matters, not just at the right distance, but with the right atmosphere, the right geology, the right history, is a question that the next decade of observations may begin to answer. Meanwhile, in laboratories on Earth, human beings have been pushing in the opposite direction. Eric Cornell and Carl Wieman at the University of Colorado and Wolfgang Ketteler at the Massachusetts Institute of Technology achieved temperatures of less than a billionth of a degree above absolute zero by cooling clouds of atoms with precisely tuned laser light and magnetic traps, a technique that strips thermal energy from atoms with extraordinary precision, producing states of matter called Bose-Einstein condensates, in which quantum mechanical effects become visible at macroscopic scales. Temperatures the natural universe cannot produce. Colder than the deepest supervoid. Colder than the permanently shadowed craters of the moon. Colder than anything that has existed in nature since the Big Bang. Achieved in a room-sized apparatus at enormous energetic cost for fractions of a second before the atoms warm back up. And even then, even at a billionth of a degree above absolute zero, they could not reach the floor. Absolute zero itself is not achievable. Werner Heisenberg's uncertainty principle guarantees it. Even at zero temperature, quantum mechanics requires particles to retain a residual motion, zero-point energy, an irreducible quantum vibration that cannot be removed by any physical process. The floor has no floor. Cold has a limit, and nothing can reach it. The cold you feel on a winter morning is not space. It is air, molecules pressing against you, taking what you have. Space does not take. It offers nothing back. It is the universe at its most characteristic, indifferent, vast, and overwhelmingly cold. Look up on a clear night. Every point of light you see is a thermal exception, a pocket of fire holding against the cold for a span of time that, measured against the universe's full future, is barely a flicker. The cold was here before the stars. It will be here long after the last one goes out. It is not coming for you. It is simply waiting.